Hi, so yeah, this work is collaboration with a bunch of people at NYU in Courant and Center of Data Science. And we're basically interested in applying some of these graph neural network methods that Max actually mentioned earlier in his talk to the problem of inferring sort of what happened in the middle of the Large Hadron Collider when you measured some experiment. So just to preface this, I'm not a physicist, so if I butcher the physics, please go easy on me. So the basic idea of this is that we want to combine both physics knowledge and machine learning ideas. So we're going to import physics knowledge, also some algorithms, and then who knows where it's going to take us. So just a primer on jet physics. The Large Hadron Collider is in Switzerland. I'm sure you all know about it. And they're colliding particles around and around together and looking to observe interesting new physical phenomena. And so this is a kind of typical picture from the ATLAS experiment. So if you look in the middle, how does this thing go? If you look in the middle, that's some collision that happened. And then there was a sort of spray of particles going outward. And you see on either direction, they kind of agglomerated together or clustered together to provide these two kind of sprays in either direction. And these are known as jets. Now, you don't actually see what happened here. All you see is the stuff that was measured on the outside. And so at the microscopic level, you start with some particles, and you can calculate those from first principles, how they interact with each other. And then you calculate some more interactions. And the particles sort of multiply and collide and destroy each other and so on. And you end up with yet more particles. And this looks like quite a lot, but actually it's even worse because this is the big picture, which is if you look at the yellow thing, this is a calorimeter here. And this is going to measure the particles which are sort of whizzing out here and they get buried here somewhere. And it's also going to measure their momenta, their energy, and so on. And where does that microscopic picture fit in? It's kind of in the middle of that circle. And it's much, much smaller than that. So you have a lot of sort of quantum interactions happening here and particles that you can't really measure. And then some stuff sort of gets buried here, kind of blood on the wall, and you want to see who did the murder or something. And the advantage of current physics is that you can simulate this interaction. So although you actually don't see what happened in the middle, there exist powerful physics simulators that can start with these particles, these red dot here in the middle, and propagate the forward model and simulate what happens at the end, and simulate the interaction with the detector, simulate how they get buried in the calorimeter, and so on. And so given that, we can take a bunch of we have a bunch of input-output pairs. So the problem that we're going to study, there's lots and lots of problems you could talk about here, but the specific one we're looking at is classification of W bosons. So here the input is the set of jet constituents, the momentum estimates. So you have some collection of n particles that got buried in the detector somehow, and you have measurement of their form momenta. And you want to infer, well, what was it in the middle? What happened at the start? And this is either going to be a W boson, or it's going to be some quark or gluon QCD event that's background. And I'm told that there's roughly 1,000 background particles, background events for every W boson. We want to classify these kind of big clusters of particles into what was the progenitor particle of the jet. So this is just a binary classification problem. It's just bread and butter for people in machine learning, and you can use a lot of different ideas to solve this problem. So I'm just going to look at some previous kind of analogies that people have used and ways that people have taken this problem and applied machine learning to it. So the first idea is what are called jet images. So in this work, what you're going to do is you're going to take the stuff that collated on the outside and project it somehow onto an image space. And now if you imagine you have this kind of big round sort of cylindrical image, it's not like a square image, but maybe you could cut it and then unfold it, and now you have some sort of image. And then once you have an image, you can apply a convnet to it, and that sounds like a good idea. And you can get some pretty interesting results with these kinds of things. One of the issues with a jet image approach is the jets are incredibly sparse. So, they're not like your average picture of a cat or something. They just look like a few dots. So, as you might imagine, like the traditional image classification approaches maybe aren't best suited for these kind of incredibly sparse images, and you maybe have to get some bells and whistles to come around this. And this is kind of the average image of the background and the average of the signal, and you can see it's kind of hard to tell the difference between them. I mean, if you look really, really closely, you can see that they have a subtly different radiation pattern. So this one, the W jet on the right, decays sort of more quickly from red to blue, and this one is a bit slower. But you can see that there are some issues with applying image recognition. Now, you might also look at the idea of clustering the particles. So here the idea is, well, you have some generative process, some forward model, which took some particles and they made it some other particles, which made some more particles, and you see the stuff at the end. And now you can say, well, can I reverse that process, maybe through some clustering algorithm, and build some kind of tree which will lead hopefully back to the source of the original progenitor particle. And these things are called sequential combination algorithms. They're basically greedy clustering algorithms that are going to have some distance metric on the particles that you currently have and take the two ones that are nearest to each other and just cluster them together and then repeat. And you have a number of different metrics that you can apply, and these are called Cambridge-Arkin, KT, anti-KT, which are physics motivated. So you have some physics motivated idea of the distance between the particles, between the measurements of the particles, their form enter, and you cluster on the basis of that. And this is neat. It gives you a binary tree representation, which means that it suddenly looks like a parse tree. It looks like a sort of NLP type problem, where you have subject phrase, noun phrase, and so on. And which means you can now use NLP methods that you would use on parse trees. So this motivates the recursive neural network, which is some other previous work that provides an extremely strong baseline. So just to briefly review what the recursive neural network is doing, given some nodes in the tree, so let's say you have, here is the parent node, and you have these two children. What it's going to do is it's going to compute its representation of this node based on the representations of these two nodes, and maybe plus some input data that you have tagged at that node. And you'll apply the same recursive function at every level of the tree. So this is some kind of NLP's type method, and this is what the equations look like. So you're going to have, to compute your new state y, if it's a leaf, maybe you just have some u, which is like an embedding of the data of the leaf. And if it's not a leaf, then you're going to take the representation of the left child, the representation of the right child, and then the representation at that node, and combine them and make a new representation. And you apply this at every single level the same way. So you induce some kind of self-similarity, some inductive bias into the network that there will be self-similarity. This provides a very strong baseline for this work. And then the idea is that what you'd do at the top is, okay, so where's the classification here? There isn't actually any classification yet. What you'd do is you'd compute, if I go back to here, you'd compute the representations at the bottom and propagate them all the way up to the top. And then at this big red node here, you have some representation, and then you're going to use that to classify. So you just plug a classifier onto the top of that. So what we're doing is, very much inspired by this sort of proliferation of graph neural network algorithms that have come out. The work, I guess, goes back about a decade, but very, very recently there's been a number of papers that have been trying to work on graph structured data. So we're going to look at the particles as a graph. And what we'll say is, well, you have this collection of, 100 or 200 particles. And just like in the recombination algorithm, you can have some distance metric between them, and that naturally makes them into a graph. So you can now use some kind of graph neural network to analyze them. And this is kind of what they might look like. These blobs represent particles, and this is according to some metric of distance. this is maybe what they look like. And so you could see, this thing and that thing are that distance apart, and these things are close together, and so on and so forth. Now, just to review graph neural networks, I know that Max mentioned it earlier, I'll mention a little bit more detail. A graph neural network works as follows. It's very much like belief propagation, Loopy belief propagation. So let's say you have some hidden state at your node F, and you want to compute its new hidden state. What you're going to do is you're going to look at its neighbors, and each neighbor has its own hidden state, and it's going to send out a message, which you'll maybe get a neural network and apply that to the hidden state. And each node, let's say G, has its message that it's computed, that it's going to send out. But it's not going to send the same message to every node. It's going to send its message to other nodes weighted by its adjacency with those nodes. So what we're going to do is we're going to compute the adjacency matrix, apply that to those nodes. And so in the case of G, that was a very strong connection, so it's really F's going to get really the whole of that message. And in the case of, let's say, node E, this is a lighter connection, so that will be a weak message. So now F receives all of these messages from its neighbors, and it now updates its state. And we're going to update just using a simple GRU, where we have its existing hidden state, and it's going to take the sum of all the messages that it received and then update. So this is how it works in just presented as pseudocode. So we're going to initially embed the data, and then for a number of iterations, we're going to compute messages based on the adjacency matrix, and then update the hidden states of the vertices, and then apply this for T iterations, which you can think of T iterations, I suppose, as being T is the receptive field of these nodes. So if you apply more iterations, then each node will be able to receive information from more and more of its neighborhoods. So the first iteration, it will receive information just from its neighbors, and then it will receive its mutual friends, and so on and so forth. And then finally, you have some collection of hidden states across the graph. You want to collapse this to somehow a hidden state that represents the whole graph. And so you might, let's say, take the mean of all the hidden states, or you can do something more complicated. And then ultimately, you apply a binary classifier on the top. There's a problem, which is, where does the adjacency matrix come from? All we have is the input, which is just a set of form elements. We have, 5 minutes, okay. We have a bunch of form enter, and what's going to happen? Well, we don't know. So one option is you can use a physics-inspired adjacency matrix, such as these distance metrics that we had before. The bonus here is that you import some physics knowledge. The other option is you can learn the matrix from the data. So this is what we're going to do. We're going to learn the interactions between each of the particles and predict a weight between each of the particles. And then that we will use as the distance. So how do we do this? Well, we just apply some kind of symmetric function f to each of the hidden states. So you could take something as simple as just summing two states together and multiplying them by some vector and adding a bias, or you can, there's these sort of dist-mult things which use tensor factorization. There's also this Siamese network where you could just compute the norm between the vectors and try and induce symmetric that way. But anything will do. And you're going to compute a score for each pair. Then you're going to take a softmax over these scores, and now you have an adjacency matrix. And by taking the softmax, we ensure that every node has in degree 1, but it might have out degree more than 1. And if you wanted to have an undirected graph, you could just sum it with its transpose, and now your graph is undirected. So now we've learned this adjacency matrix. The algorithm looks as follows. It's exactly the same as before. The only difference is that we're going to learn this adjacency matrix. And we're also going to untie. You see there's a little t here. We're going to untie these things. So rather than viewing it as tied weights, we could consider this as a number of layers, where we're learning perhaps different matrices at each layer. So there's different metrics at each layer, different kinds of messages at each layer, which might take in more and more interesting information, different kinds of information at each step. So just moving on to experiments, what we did was we took some data from this Pythia event generator. So this is the thing that simulates these events forward. And it's the same as in the recursive neural network baseline. We take the following amount of training examples, or although it's actually a little bit less than that because we have to crop some of them out. And we have balanced classes, which is not like how it would be in the real world. In the real world, it's like 1 to 1,000. Here we have 50-50 signal background. So because we get to simulate, we can do whatever we want. And the metric we're going to use is we're going to take the background rejection rate at the true positive rate being 50%. So the motivation here is, well, we want to have a high amount of rejection, a high background rejection for a given true positive rate. And I'm told that this number, we want this to be order 100. So we want to be rejecting 100 noise particles for every one that we accept, given that we're taking 50% of the true signal particles in. We just train it with binary cost entropy loss. There's no bells and whistles or fancy regularization. So just taking you over some of the results. So again, just to remind you of this metric, which is the background rejection rate. So it's not out of 100. We want this to be as high as possible. It could go up to infinity. And so the previous baseline, the strongest result was this recursive neural net, a gated version of it, which could reject about 83 particles. And we're up to almost 100 now. And we have these baselines, so we use this identity message passing neural net, which just uses the identity matrix for the message passing, so there's no learning at all. And as you can see, it doesn't perform very well. We also have some relation network, which is kind of like the DMIND paper, where you just learn the adjacency matrix once, and then you make a prediction based on that. So as you can see, we're getting some pretty good results. Here's just a ROC curve. It's not particularly informative, so I'll skip over it. Future work. The problem with this approach is it's quadratic in the nodes. So you're trying to learn an adjacency matrix based on 100 or 200 nodes. And that's OK, because that releases 40,000, something like that. But let's say you have 1,000 nodes. Now you have a million things to learn. So there's a question, can we make this matrix sparse? And that would help us to apply it to larger data sets. So one approach we can do is we can try and reduce the number of nodes at each iteration by using a attention mechanism to kind of cut down that number of particles every layer. And so we might start with 1,000 particles and go to 100 and then to 50 and then to 25. And the other opportunity is we can use the adjacency matrix that just comes from physics and try and use that for message passing, which we haven't looked at yet, but I'd be very interested to see if it's also useful for classification. And then the idea is now we can export this adjacency matrix that we've learned, and now physicists could maybe use this for their recombination jet algorithms, although it has been pointed out to me that the adjacency matrices they use have to have certain mathematical properties which we do not enforce. So we're going to see if we can combine those two things. Thank you.
Thank you so much for the fantastic contribution. We have time maybe for one question, but then the authors will be around for the rest of the day. Maybe right here. Go ahead.
The matrix you're imposing connects every node to every other node by some weight. So it's like no local information beyond the small weights for some pairs and large weights for some pairs.
Yeah, that's right. It's a fully connected graph, and we're just learning the weights between that, which has that problem. We want sparsity in the graph. But yeah, we don't make any assumptions about what nodes are close to others. We're learning that.
That might be a way to speed it up and project it in some space and do local operations.
Yeah, well, we're looking at how we can detect these kind of local things and try and hopefully do it automatically, although we could use some physics knowledge to try and, there are physical ideas about how you can cluster these things as well. So we could use physics, or we could use machine learning, or maybe both.
Thanks.
All right.
Thank you again, Isaac.